10.9, energy and collisions. So from chapter 9, we know if no external forces act on the object's momentum is conserved in a collision. So now we're going to study what happens with the energy in a collision. So we have two train cars moving towards each other. They collide, they couple together. We use conservation momentum to find the final velocity. And from the given initial velocities, how much thermal energy is created in the collision. So before and after visual overview of the collision between the two train cars. So before we have the masses, we have the initial velocities and train car 1 and 2. And then after they've coupled together, we're told that the final velocity is negative 0.25 meters per second to the left then, and mass 1 plus mass 2 is the combined mass. So what do we do?
Well, first off, we need to use that energy diagram that we used to have that I can't remember.
The work energy
Yeah.
equation. So what would we have in this problem? We have kinetic because we're still moving. So final kinetic.
There's no potential anymore.
On the left side still, we're caring about the thermal energy. So delta energy thermal. That's how we write that one. Equals.
K sub I.
Yep.
And there's no work done.
No work done, and that's it. There's no potential. So that's it. That's the whole equation. So we're trying to find thermal energy. So we're going to move the kinetic final to the other side. So we have delta thermal equals K initial minus K final. Okay. And what is kinetic's equation?
1/2 mass times velocity.
1/2 mass times velocity squared. Okay. So we have delta, just giving myself some more room here, thermal equals, now kinetic initial would be the two separate cars in the system both have kinetic initial, right?
Yeah.
So we got to account for both of those things. So I got to write really small to make this all fit. So for the first car, we're going to have 1/2 mass.
4.0 times 10 to the fourth.
All right, so I'm just writing down the formulas first. So mass 1
times velocity 1 initial.
Velocity 1 initial squared.
Plus mass what? Yeah, mass 2.
1/2 mass 2.
Oh, okay.
Velocity 2
squared.
initial squared. Okay, now that takes care of kinetic initial.
And then kinetic final is going to be just mass 1 times plus mass 2.
Good. 1/2 though, and then mass 1 plus mass 2 together, and then velocity final squared. Okay. So now we got to plug all those numbers in to get the initial kinetic energy, and then plug all those numbers in to get the final kinetic energy, and then subtract them. Okay.
Yeah.
Now I really don't have a whole lot of room here to do all that. So let's see what we can do. I'm going to have to squeeze pretty tight. So we got 1/2 mass 1.
2 times 10 to the fourth.
Okay. And then V1.
1.5 meters per second.
And that's squared. Plus 1/2 mass 2.
4 times 10 to the fourth. Times by negative 1.1 meters per second.
Negative 1.1, yep. Okay, does that take care of everything?
On that side.
Yes. Now, do I need the brackets with order of operations? No. Okay, so I'm just going to go down to a second line here. Minus 1/2. Now, mass 1 plus mass 2.
So 6 times 10 to the fourth.
Can we do that?
Oof, no, we can't, can we?
Okay, times.
Negative 0.25 meters per second squared.
Oops, I forgot my square right there. Okay, meters per second squared.
And we can plug all that into a fancy calculator.
Yes, plug it all in. Let's see what we get. 44825. What?
It's gonna be joules.
Joules? We're trusting it's joules.
It's energy thermal.
We have two significant figures, so 45,000 joules. Here's your answer. Okay. So is that a lot, a little? What are we doing here?
Yeah, it seems like a lot of joules.
A lot of thermal energy in the collision.
That's crazy.
I guess.
And they weren't really moving very fast either.
Yeah.
So I wonder how much thermal. Well, yet again, the mass
don't know
plays a
how
big
much
effect into it too.
Energies. I don't really know how much energy is in 1 joule. Like, is there like a, like a representative that you could show me, like rubbing my hands together or something for a second?
Can you convert joules to watts or something like that?
Watts of power.
Okay, so
What is joules?
what about volts?
Volts?
Did you hear that?
Just
I did hear that. What was that? Ooh. All right, elastic collisions. So in the figure, the tennis ball is colliding with the racket, compressing the ball and stretching the strings on the racket. Then the ball expands and the strings rebound as the two are pushed apart. In terms of energy, the kinetic energy of the objects is transformed into the elastic potential energy of the ball and the strings. So this is acting like a spring situation. And then into kinetic energy as they spring apart. If all the energy goes, all the kinetic energy goes to potential, and all the potential energy goes back into kinetic energy of the objects, and then the mechanical energy is conserved. A collision in which mechanical energy is totally conserved is called a perfectly elastic collision. So most real collisions fall somewhere between perfectly elastic and perfectly inelastic. A rubber ball bouncing on the floor, the super bouncy balls, might return to 80% of its original height, then losing 20% of its kinetic energy per bounce. Okay, quote unquote, losing 20% of its kinetic energy per bounce. Two pool balls or two steel balls, so just basically very hard objects, come close to being perfectly elastic. So if you picture pool balls bouncing off each other, those are very elastic collisions. They lose almost no of their kinetic energy. So do collisions between microscopic particles. So like atoms and electrons, almost elastic. Okay?
So when atoms collide and stuff like that, is that causing thermal energy? So the Earth itself is just caught.
Have you ever seen a nuclear warhead?
Have you?
No.
All right. So a perfectly elastic collision in this picture. Before we have 1 approaching 2 with V1 initial. During the collision, we have 1 colliding with 2. And then after we have 1 and 2, both with a V1 final and a V2 final. So the kinetic final equals the kinetic initial in this. Energy is stored in compressed molecular bonds here and then released as the bonds re-expand. The kinetic initial that we had equals the kinetic final in the end. That's the key for the perfectly elastic collision. We lost nothing in the process. So that's a head-on perfectly elastic collision. Everything's moving in the same direction in the beginning and the end. We have no angles to deal with. The collision must obey 2 conservation laws. One is the conservation of momentum, chapter 9 stuff, obeyed in any collision, and the conservation of mechanical energy. So that is because the collision is perfectly elastic. So note that it's possible for ball 1 to actually bounce backward in this case. So although energy is transformed into potential energy during the collision, the mechanical energy before and after the collision is purely kinetic. So therefore we have these 2 formulas. M1 V1 initial equals M1 V1 final plus M2 V2 final. And this is because M2 was stationary. Okay. In the second one, we have 1/2 m1 v1 squared initial equals 1/2 m1 v1 squared final plus 1/2 m2 v2. Should I have a squared on that too?
You should.
Probably.
And that's because M2 was moving this time?
Yeah. So what is this law here that we're talking about?
It's potential.
That's not potential. That's conservation of momentum. Okay. What is this law here that we're talking about?
Conservation of energy.
That's conservation of energy. Okay. So this is momentum, and this is energy. Okay. Both of those must be satisfied.
In order for it to be perfectly elastic.
Yes.
So if one isn't satisfied, then
if it's a perfectly elastic collision, then both are satisfied. Okay, so which means we can use both equations. Got it?
Yeah.
Okay. So the algebra to find the final velocities of the two objects when object 2 is initially at rest, which was the equations that we're looking at, is just straightforward. But it is kind of cumbersome to deal with, so I just eliminated that process and just gave you these. So here are the results. The V1 final is this. Oh yeah, hey, look at that. This is mass 1, not mass exclamation. And V2 in the final situation is this. So that makes it a little bit easier. All right, so an example on the air hockey table, moving puck traveling to the right at 2.3 meters per second makes a head-on collision with an identical puck at rest. What is the final velocity of each puck?
So we're going to
probably use those equations.
Probably use those equations? Okay.
We don't
The
got to use
momentum
both. We
one.
only got to use the first one because the masses aren't sticking together, correct?
Yeah, they won't stick together.
So we would use the first equation.
So we need V1 final and V2 final.
Well, you know, velocity initial for one puck is 0, velocity initial for the other puck is 2.3. So velocity 1 final is equal to, let's see, I don't have the masses.
What will the final velocity of the first puck be?
0. Wait.
Yeah, it would be 0.
It will be
Because they
0.
have the
Okay.
same mass.
Because they have the same mass. So just look at the first equation. M1 minus M2 right here. Mass 1 minus mass 2
Oh, no, the same.
gives you 0 on top. So that thing turns into 0. So V1 final is 0. If you ever played pool and you hit the ball, the cue ball, with no spin directly at another ball, the cue ball stops.
Because they have the same masses.
And then
Okay, now this one does not have the same situation on top. So this will be different, okay? So V2 final, we have 2 mass 1,
and then
Which is,
and I'm just going to call it mass because they're the same. Divide by M1 plus M2
So
mass
2M1.
is 2M again.
and then
So that's 1.
times by your
velocity, which is 2.3, so it's going to end with 2.3.
Yeah.
Because the velocity is
So the two masses divide out there, and we're left with velocity initial times 2 divided by 2, which is just velocity initial. So that is 2.3 meters per second.
homework.
Having the formulas worked out is definitely to your advantage.
Thank you.
Uh-huh. All right, so one more thing. The small ball with mass M, capital M, is at rest. It is then struck by a ball with twice the mass moving at speed v naught. The situation after the collision is shown. Is this possible?
It's V not. You mean like V is equal to 0?
V sub 0 is
No velocity.
v naught.
So velocity doesn't exist.
No, it means an initial velocity, whatever the initial velocity is.
Okay. Well, it says. Oh,
So what do you think? Think about it for a sec. Any ideas?
Yep.
What?
D.
You think it's D?
I agree.
Neither momentum nor energy is conserved. We got to be sure about that. So let's look at momentum. What would the momentum equation be?
I was looking at the V2F equals 2m1 over m1 plus m2. V sub
Okay,
I.
so you're looking at not momentum.
Which one was that?
Let's look at momentum.
V sub I is equal to mass 1 times velocity 1 final.
So for the momentum one, we need the mass times velocity plus the mass times velocity equals mass times velocity plus mass times velocity, right?
Mm-hmm.
So what would it be for this situation? In the before and the after. So mass times velocity of one of them before plus mass times velocity of the other one before.
Well,
So for this one, we'd have two masses
times the velocity.
times velocity.
And then the other one's just going to be 0 because it's not moving.
So plus mv, but I'll just get rid of this, equals
to, mass times
M1 VI.
This one's velocity is 0 now, but
So,
I'll say 2 mv naught, but this one's 0. And then
2
plus 2.
M or 2 M2
It would be, okay, so I'll write it in the right order.
2V.
M M
times.
parentheses 2V.
No.
Yeah. V dot.
But it shouldn't matter if we put that 2 because
No, it really doesn't. But the mass is
the same.
Is the mass the same or is it half?
No, it's 1/2.
It's 1/2. So am I writing this right? It's 1/2 here, right?
Mm-hmm.
And this is 1/2, but it's times 2
Yeah.
v. Okay. All right. So
You would end up with MV equals 2 MV, which is impossible.
but it's squared. The velocity is squared, isn't it?
No.
Yes, it is. No, it's not. I think it was the wrong thing. So let's see. We have 2 mv naught. This one's gone. This is not 1/2 here. Sorry. This 2 mv here is not there. And this is not 1/2 here. It's just m.
Yeah.
Okay. So 2 mv and 2 mv. So momentum is actually conserved.
Well, it is when you do that like that.
Well, because I'm doing it right. Okay, so momentum is conserved. So
That rules out.
momentum is not conserved? No. Momentum is, okay, so no. So it's either A or C. So now we got to look at
Energy.
the energy being conserved, right?
And this is the 1/2.
So this one's the 1/2 m, but it's 2m,
V.
and then v squared. So that was v naught squared for this guy. Okay, and then we have plus 1/2 m for this guy,
Yep.
v squared,
Which
but
is
this one's 0,
Which is
equals
And it's going to be the same thing, 1/2, 2m v naught squared.
1/2 the 2m v squared for this guy, but it's
0.
0. and then plus 1/2 just m. And now he has the 2v naught squared. Okay, what do we see?
Yeah.
This would be, this one on this side turns into just mv naught squared.
Yep.
This one, these two are gone.
That one turns
This
into
is 4.
so that's 2mv naught.
This is 2mv naught squared. We don't have an equal situation. So energy is not conserved.
Yes, I knew it.
You said the wrong thing.
Yeah. You know something I noticed about that beeping?
Okay, so momentum is conserved, energy is not conserved. The answer is C. All right, so that's how you do that. I kind of fumbled it around a little bit, but I got it right.